let's continue with using calculus to find the area under a curve. In the video I recorded just before this, I sort of gave just a slight sort of background on how calculus was developed to help solve this problem. I guess from reading the books, this is an issue that maybe mathematicians hundreds of years ago, they were trying to solve, where they were taking a region under a curve, and then in this case, the bottom of the region is just the x-axis. And they were trying to figure out a mathematical way to find the area of this region. And eventually, they developed what's called integral calculus, where you can use calculus to find this area. And in the last lecture, we talked about sort of the idea that you break this up into very skinny rectangles, and you add up all the rectangles and do a limit. Lo and behold, you come up with the integral as a way to find this area. So if that kind of thing interests you, you can go online and get all kinds of in-depth teaching, or even look in the book. What I thought I would do now is just do some example problems that you're going to see in the homework, and probably eventually on a quiz and a test. So, and what I'm going to do is I'm going to actually, for instance, here's the first problem. The curve we're looking at is x squared. We're going to try and find the area under this x squared function that's above the x-axis, but beneath this equation. And along the x-axis, we want to go from 0 to 5. What I'm going to do is I'm actually going to, well, actually, I created a graph here, because sometimes in calculus helps to visualize things. So here's a graph of x squared. So now we're going to go from 0 to 5. So here's 0. And here's 5. Just to make this not too messy, also draw a dashed line here at 5. So we're going to use this integral to find this area. Matter of fact, I could probably just do it right here. So this is a definite integral because we have both a lower and upper limit here. The integral of x squared, pretty straightforward, right? You add 1 to the exponent, put the new exponent on the bottom, and we're going to evaluate that from 0 to 5. So you put in the top number for x, and then you subtract when you put in the bottom number for x. Now on the specific homework problems, you'll have to look. Sometimes they may want an exact answer, which means you don't round off your decimals, but sometimes they do want you to round off. For this one, 5 cubed is 125. Now 3 does not go into 125. So sometimes if they want an exact answer and don't want you to round off, that might be your answer. But other times they will tell you to round off to like 2 or 3 decimal places. So if I actually divide this out, 41.67. Now what's interesting, and we're not going to do it, but basically it's saying, if you look here, you have to be careful because along the horizontal axis, it's like this is 1, this is 2, but moving up. So for instance, right here, even though it looks like a rectangle, that would be an area of 1. So if I were to take the time and to sort of try and add up all this area, when I'm all done, I should add up almost 42 squares of 1 by 1. All right. Hopefully you can see this is a lot easier than trying to break this up into rectangles and find the area of each rectangle and add them all up, right? That would be a nightmare. This wasn't too bad. How about the next one? This looks pretty similar actually, but it is a different equation. Above my graph is the equation. This is the equation of x squared minus x. So the problem they asked us about here was they want us to go from -1 to 4. The function is x squared minus x dx. Now let me just point out something. You notice in this case, we just have a little bit of the area that is beneath the x-axis. So we're trying to go from -1 to 4. I just draw my dashed lines. Well, this one's pretty straightforward. I guess this one is too. So this is going to be the area. So I got this over here, this up here. But I've got also a little bit of area underneath the x-axis. So what's up with that? Well, as it turns out, we're going to just solve this integral problem. But just so you know, in this case, when the function is above the x-axis, all these areas are considered like a positive area. Just like the one I did a minute ago. In this case, the function was above the x-axis, so this ended up being a positive number. But what's interesting, anytime the function or the graph is below the x-axis, when we calculate this area, we make this area into a negative number. So if you have any area beneath the x-axis, we consider that negative. It's almost like, you know, when you go below the x-axis, your values of y are negative. Well, if we have any area beneath the x-axis, we consider that a negative area. Now, the nice thing is I can just go ahead and solve this integral. I really don't need to worry about any of this. As a matter of fact, normally you may just be given the problem like this and you just can solve it mathematically. I'm just giving you the graph just to make it more interesting. The good thing is, so even though Two of these regions have a positive area and one of the regions has a little bit of a negative area. You can do it. If someone wanted to, they could find the area of this part, area of this part, and the area of this part. And then you add them together and you would make the area of this part a negative number and you would get the answer. But the nice thing is we don't have to break it up into three sort of different regions. I could just do the whole thing all at the same time. So let's go and do it. So now I have two terms here, but both of them are going to follow the power rule. So x squared becomes x cubed over 3 minus x squared over 2. I'm going to go from -1 to 4. Now, sometimes in these kinds of problems, they can get pretty messy because you end up with a lot of fractions, a lot of exponents. Just be careful with your math. So I'm going to plug in 4 for x. And a lot of times I put all this stuff in parentheses because it can get messy pretty quick. So 4 cubed over 3 minus 4 squared over 2. So that's when I plug in 4 for x. Now I've got to subtract. Now I'm going to plug in -1 for x. So -1 cubed over 3 minus -1 squared over 2. So now it's just a matter of doing this pretty messy math. 4 cubed, 4 times 4 is 16, that's 64. So I already have 64 over 3. 4 squared over 2, that's 16 over 2, hopefully. I don't mess up. So 64 over 3 minus 8. Minus -1 cubed is -1. So this is -1/3. Minus -1 squared is 1. So this is -1/2. Now, you know what? I'm going to go ahead. If they ask for a decimal answer, you could just grab your calculator and do this calculation, but just for fun, I'll do it the old-fashioned way. I'll try and find a common denominator. I've got a 2 and a 3 and a 1 and a 3, so a common denominator is going to be 6. This first fraction multiplied by 2 over 2, 128 over 6, here multiplied by 6 over 6. Now here, the 1/3, I'm multiply top and the bottom by 2, so it's really going to be -2/6. But I'm going to subtract a -2/6, which means +2/6. Then 1/2 multiply top and bottom by 3, so 1/2 becomes 3/6. So I'm going to subtract a -3/6. So now I'll try and do this in my head, but 128 minus 48 should be 80. 80 plus 5. As a fraction, it's 85 over 6. I guess there's two ways to write it. You could change this into what we call a mixed fraction. So 85 divided by 6. 6 goes into 85. Should be 14. So 14 times 6 is 84, and there's 1 left. So we could say it's 14 1/6. And if you wanted to give a decimal answer, 85 divided by 6, 14.17. All right. So I'm telling you, I mean, the calculus part is pretty simple. This algebra part, adding, subtracting, converting fractions, be careful what you're doing because that messes up a lot of people. All right, a couple more examples. Here's one that we have a lot in calculus just because this function is used a lot. Look at my function, e to the x, the natural exponential function. All right, it gets used a lot, so we're gonna have a problem. So here's the graph of e to the x. It's interesting how as x gets smaller and smaller, it's like an asymptote. It never quite ever touches the line. But this actual problem is just gonna be find the area under the function e to the x from 0 to 2. Where 0 is right here, 2 is right here. We're going to find the area of this. Now, if you recall, the integral of e to the x, it's just e to the x. It's a definite integral going from 0 to 2. So e to the 2 goes in for x, and then 0 goes in for x minus e to the 0. Now don't make the mistake that some students do. E to the 2, what is e to the 0? Well, anything raised to an exponent of 0, it's actually just 1. Don't think e to the 0 is 0 because it's not. E to the 0 is 1. Now, if they were asking for an exact answer, that would be it. If they're asking for a decimal answer, you can grab your calculator and find e to the 2 and subtract 1. 6.39. All right, this may have been the easiest problem also for it because the math wasn't very messy. All right, last one. Although actually I'm going to do 2 problems with the same function. So you can see from the graph, this is one of those where there's 2 different pieces. This is a graph of y equals 1 over x. So the first one I'm going to do, I want to go from 2 to 5, 1 over x dx. So from 2 to 5, oh, you know what? I have a bad graph here because I can't, you see here's 1, 2 over 5 is way to my right. So we can't visualize it. But I hope you can imagine as this graph just starts to level off. You go to 2 and you go to 5 and you've got some area underneath it. So let's just go and solve it, even though I don't really have the picture of it. Don't forget, this is a special integral. What's the integral of 1 over x? Natural log of x. Now here's what's interesting. This isn't really quite the right answer. And with the next problem, you're going to see that it matters. It's actually natural log of absolute value of x. So now if I evaluate it from 2 to 5, natural log of 5, plug in 5 for x, absolute value of 5 is just 5, minus natural log of 2. Now, if they were asking for an exact answer, then you're done. But if they want us to round it to a decimal, then I could take 5 natural log minus 2 natural log 0.916. Interesting. So it's actually a pretty small area. I think by the time you get out here to 5, this functions end up being pretty close to the x-axis. Let's do a second problem, which is even a little more interesting. How about the same function, 1 over x, but now we're going to look at the area from -4 to -1. -4 is right here. -1's right here. That's going to be the area we're looking for. Now, based upon what I said a few minutes ago, when we finish this problem, what are we going to be looking for in terms of this area? Well, that's not a very specific question, but what I'm trying to get at is, since this area is below the x-axis, I'm going to assume this area is a negative number. It's a negative area since it's below the x-axis. So let's see if that's what happens. So the integral is the same. Integral of 1 over x is natural log. Now this case, absolute value is going to become important. Because if I plug in -1 for x, and then plug in -4 for x, now, what is absolute value of -1? Just 1. What's absolute value of -4? 4. So that is an exact answer. If they want a decimal, take 1 natural log. Well, some of you may have known this, but the log or natural log of 1 is always 0. So this first term is 0. So I'm going to have negative natural log of 4. So equals approximately 1.386. So in fact, it's true. This is a negative area, negative 1.386. All right. I mean, it's not any worse than that. Find the area under a curve. The key is you're going to use the x-axis as your bottom level. And then you're going to see the area above the x-axis onto your function. Or if it happens to be, to get to your function, you have to go negative, then it's going to be a negative area. All right. Not too tricky, I hope. So hopefully you can figure out all the problems that you have to do.